Yeah, so, well, thanks a lot for the invitation. It's a pleasure to be here. Since it's, kind of informal setting, so you should certainly feel free at any time to interrupt me and kind of have the discussion go off onto a tangent. So what I want to talk about in these three talks, so today it's mainly going to be kind of motivational and some overview of the kind of results and the broad overview of the kind of techniques used to prove them. And then the next two talks I'm going to go more into the actual math of how you do it. So let me just first start by explaining a little bit what it's all about. So let me just start by recalling what people mean by the Φ43 model, so the usual kind of static Φ43 model. So of course, I mean, the audience is very disparate. So some of the audience were there at the time, and so I'm not going to say anything to them that they haven't known for 25 years. But then there are also younger people in the audience who probably don't know about that stuff. So
maybe some older also.
Right. So formally. So what is this model? You should think of it as being a measure on a space of distributions. Okay, so you have a measure mu, which would be a probability measure on, say, distributions. And in all of my lectures, it's going to be distributions on a finite volume. And so I'm going to put it on a torus, so I don't have to worry about boundary conditions. So it's Schwarz distributions on the three-dimensional torus. And formally, this measure, you should think of it as being the following. So mu of d phi, phi would be your distribution. You should kind of think of it as exponential of minus a half, well, I'll say integral of a half gradient phi square plus phi to the 4, and then maybe minus a constant phi square dx, and sort of here d phi. Okay, so you should think of it as being the measure on distributions that has this density with respect to Lebesgue measure. Okay, of course, there's no Lebesgue measure on distributions, and for a typical distribution, none of these terms makes any sense, right? You're not allowed to square them, to put them to the power 4, take gradient squares. Now, on the other hand, quadratic terms, I'm looking at scalar. It doesn't really matter, but take scalar. Right?
Is it normalized?
Okay, it's a probability measure. Now, quadratic expressions, we kind of know how to make sense of them, right? So we know that a Gaussian measure has density e to the minus 1/2 times the inverse of the covariance, blah, blah, blah. And so I should really think of this as exponential minus integral of just phi 4 minus constant phi square dx times sort of p of d phi, where p would be a Gaussian measure with covariance. Well, this here, the integral of gradient phi square, I can rewrite it, so integral of gradient phi square dx, or say a half. I can view this as 1/2 of phi Laplacian phi, right? And now just by analogy with usual Gaussian measure, I say, well, this should be the inverse of my covariance, right? So this should be a Gaussian measure that has as a covariance the Green's function of the Laplacian. If you want the inverse of the Laplacian, should be the covariance of this measure. Another way of writing this would be to say that if you take under P, so the expectation under P of phi tested against one test function f times phi tested against the test function g should be f inverse of the Laplacian g, right? And this expectation would be the expectation just under the measure p, okay? So now there's absolutely no problem in making sense of it as a measure on distributions. So we could say, well, okay, so it should be the measure on distributions that has this density with respect to that measure, again with a normalization constant. And of course, the problem is that even this still doesn't make sense, right? So phi under this measure, phi is typically not going to be a function, so it's going to be a distribution, and therefore, these integrals here, they diverge, okay?
You have a small problem with the zero mode too here.
And there's a problem with the zero mode here, yeah. Of course, we're in the box, we can just mod it out or something.
What's the significance of the fourth power?
It's the lowest power that isn't a square.
I understand.
Yeah, so it's,
Does it go reason that that's
no, so that would just be it's a toy model, it's the simplest example, which is non-trivial, which would not be given by a Gaussian measure. Now,
We believe that any other power will actually
and would
go back
to this one.
Power. That's about it.
So, okay, so now there's the big results of constructive quantum field theory in the 70s or 80s were essentially to make sense of this measure. And there are several ways of making sense of this. One way of making sense of this is you could put an epsilon here, right? Essentially meaning that here, instead of taking the Green's function of the Laplacian, which has some singular behavior at the origin, you replace it by some regularized version of the Green's function, which doesn't have the singular behavior at the origin. You just smoothen it out at a little small-scale epsilon. Then there's no problem. Then under this measure, almost surely everything is functions. Okay? And then what you have to do is you have to make this constant here depend on epsilon. Okay? And the result is that if you choose this constant as a function of epsilon in the right way, the sequence of measures that you obtain in that way, well, converges or is tight. Also, you get some bounds that are independent of epsilon. Okay? And actually, the way the constant has to be chosen is if epsilon is essentially the length scale of the regularization, the constant depends on epsilon, essentially like 1 over epsilon plus a log epsilon. Okay? It kind of depends. It's in 3 dimensions, yes. Oh, yes, yes. So this is all in 3 dimensions, yes. So in 2 dimensions, essentially the same picture holds, and there's only a log. Okay? The 3 is 3 dimensions, yes. Thanks.
Which means the 2 space is 1 time.
Right. Yeah. So in the link, right. So I'm going to get back to that. So in the link with quantum field theory, that's right. So the 3 is really 2 space in 1 time. Yeah. One of the 3 dimensions is really a time. The other thing is that this quantity, so as epsilon goes to 0, you have weak convergence in the sense of measures on the space of distributions. The limiting measure that you get does not, in 3 dimensions, does not actually have a Radon-Nikodym derivative with respect to the Gaussian measure. Okay? So in 3 dimensions, the limit you get is singular with respect to the limit that you get on these measures. In 2 dimensions, even though that constant blow up, the 2 measures are equivalent in the limit. Okay? In 3 dimensions, they're mutually singular. Right. So this was, okay, so there's been a huge series of work. So it started with works of Clement Jaffe, and then Feldman Osterwalder, and then a huge number of people worked on this problem. So this is relatively well understood. And so now what I want to talk about is a natural dynamic that goes with this measure. Okay, so we have this measure, mu, which is given, if you want this, the weak limit, as epsilon goes to 0 of this. Now, suppose you're in finite dimension. You have a measure of the form e to the minus v of x dx, and now say x is in Rd, so it's something finite dimensional, not like phi. Okay? So if mu is of that form, then you can realize mu as the invariant measure of some Markov process. Okay, so what you can do is you can write down a diffusion. Maybe I shouldn't use dx. Well, okay, I'm still going to use dx. Or say x dot. So I can write down a diffusion, which would be x dot equal minus gradient v of x, which is just a gradient flow. And then, well, to make constants correct, maybe I have to put a 2 here, which is irrelevant. And here I put a psi, where psi is white noise. Okay, so take just this ODE, where you put a random input here. And psi, you should think of it now as a random distribution. No, it's just a distribution on time here, okay, because x is finite dimensional. And psi is white noise in the sense that if I take psi and I test it against two test function f and g, and I look at the correlation, I simply get the L2 scalar product of f and g. Okay, so formally, if you want, what this says is that the expectation of psi of t, psi of s, is delta t minus s, or that psi is the derivative of a Brownian motion. Okay. So now this equation you can solve, you can view it as an ODE, you can solve it pathwise, there's no problem at all, because you can view psi as the derivative of a Brownian motion, dw dt. Okay, now w is a perfectly nice continuous function, dw dt is a distribution, but then I can rewrite this as x of t is equal to w of t minus integral of gradient v of x of s ds. So if I rewrite it as an integral equation, all the terms make perfect sense. Okay, you can solve this. And what you know is that under relatively mild assumptions on v, you can start this equation with any initial condition. Okay, so you take a x0, which is an arbitrary initial condition. You look at the solution at positive time. This is going to be random because the input is random. Okay? And now if you look at the law, so here the theorem, say under mild assumptions on v, the law of x of t converges to mu as t goes to infinity. Okay, so in the sense, so you start with arbitrary initial condition, you let it run for time t, you look at the law of the solution, that gives you a measure on, say, r or rn, so x here is allowed to have n components. If it has n components, then here you should take n independent Brownian motions, one for each component. And, well, if you look at the law at time t, it's going to converge to this measure on Rn. Okay? Actually, there is some freedom here. You could put a matrix. You put a positive definite symmetric matrix here, and you put the square root of the same matrix here. It makes no difference. It converges to the same thing. So for any choice here of the matrix A, the same statement is true, as long as it's non-degenerate. Okay. So now the natural dynamic that I want to talk about is what you get if you formally try to apply this procedure here to this measure. Okay? So now here the measure was a measure on Rn, okay? And you obtain, well, an evolution equation on Rn. Here the measure is a measure on a space of distributions. So you get an evolution on the space of distributions. Okay, so now your solution is going to be a distribution-valued process of time. Okay? So what do you get formally, right? So formally, if you try to apply the same procedure, you see, well, now your dx is d phi dt is equal to, so you have the gradient of v. So v, we should think of it as being this, right? So this is v. So if I take the functional derivative of the first term with respect to phi, what do I get? So I have this gradient phi square. Okay, if I differentiate the gradient phi square into some direction h, say, I get the scalar product between gradient phi, gradient h, and then I throw half of the gradient on the other side. I essentially get a scalar product between h and the Laplacian of phi. And so the functional derivative here would be Laplacian of phi. Okay. And then for these two terms here, you get as a functional derivative constant times phi minus phi to the 4. Okay. Oh, sorry, phi cubed. Yes. Thanks. I'm minus. No, I think it's correct. There are enough. I think there are enough minuses around so that and then you have psi, which this time should be, in some sense, brown white noise, independent white noises in each component, right? So I did essentially here I did some kind of L2 functional derivative of v, okay? And so if I do an L2 functional derivative of v, I should take that corresponds to formally sort of doing pointwise differentiation at each point. And so the psi should have, well, independent, in some sense, independent white noises at each point. And if you actually think a little bit of how the units fit together, what you see is that you should take, at least formally again, psi, so that expectation of psi of xt times psi of ys is this time not just a delta in t minus s, but also a delta in x minus y. Okay, so that's this delta of x minus y, if you want, is the analog of when I said that here you should have independent Brownian motions in each component if you have more than one component. So here, in some sense, you have one component for each point in space, and so you should have somehow independent Brownian motions at each point in space. Okay. Now, you could have done the whole thing. Remember here I had this a and square root of a. So you could actually have obtained, instead of obtaining this equation, we could have done the same. This kind of corresponds to a being the identity. You could have taken a different a. So you could, for example, look at this equation, d phi over dt equal minus Laplacian of Laplacian phi plus constant phi minus phi cubed. And then here, some kind of square root, which would basically be a divergence of a psi, where now the psi is a vector-valued space-time white noise. So this would correspond to taking a equal to the Laplacian formally. Okay? And that's also a natural dynamic that you would expect to have the same measure as invariant measure. Okay? So now, why would you want to do that? So as already mentioned, if you do the link with quantum field theory, one of the space dimensions here is really time. Okay? So then there's no point of adding an additional time. There are two reasons why you would want to do that. The first reason, which is, in my opinion, of the more important one, is the one that you would also expect this measure to describe the behavior of Ising-type models near the critical temperature. And so if you have a model like an Ising model, this would describe the fluctuations of the magnetic field near the critical temperature. Now, an Ising model, naturally, space is really space. Right? And now you would want to have time in order to describe dynamical fluctuations of the Ising model. Right? And now, if you think about the different dynamics that you can have on the Ising model, well, this, to some extent, should describe the Glauber dynamic near the critical temperature, and this should describe the Kawasaki dynamic near the critical temperature. Well, if you're at any temperature, you wouldn't really expect it to be described by this continuum theory. I mean, if you're at any temperature, you wouldn't. I mean, if you're at high temperature.
Just because you're in a continuum doesn't mean you're critical.
No, but if you're at high temperature, then you would essentially just get white noise, right? I mean, things decorrelate very quickly, so you wouldn't expect it. Okay, so this would be kind of a Glauber type dynamic if you want. This would be a Kawasaki type dynamic. Another reason that was actually proposed by Parisi and Wu was to say, well, maybe these objects are actually easier to analyze or easier to describe than that object, and so therefore you might get some information on that object by understanding these objects. Okay? And so then the time would be a completely fictitious time. You don't care about it at all, and you just say, well, you know, it's a trick to get an object that you have a better handle on. So there have been sort of a number of attempts to make sense of this. It works, so in dimension 2, it works rather well. And so I think in some sense the first who managed to get a good dynamic for this was Ione Lasinio and Mitter, but then they didn't quite manage to make sense of this equation here. They had to introduce some additional regularization. So if you want, instead of taking A, the identity or the Laplacian, they had to take A like an inverse power of the Laplacian, and had to be a big enough inverse power. So they had to regularize this whole thing by some inverse power of the Laplacian and some inverse power of the Laplacian here.
So that's in
Two dimensions, yeah. Now in 2 dimensions, I think Albeverio and Röckner were the first to sort of give a rigorous construction of this object by using Dirichlet form techniques. But then in some sense it went kind of counter to the spirit of Parisi and Wu, because they needed to have a good handle on the measure in order to be able to build the Dirichlet form. And so it wouldn't really say so much about the measure, because they already used a lot of information on the measure in order to build the Dirichlet form. And in particular, they used very strongly the fact that the measure is equivalent to the Gaussian measure, so that you really have a density with respect to the Gaussian measure, which is true in dimension 2 and is not true in dimension 3. Yeah. And then more recently, there's a work by Da Prato and Debush, where they also looked at this in 2 dimensions. And their construction would work for that equation as well, and probably the one by Albeverio and Röckner as well. And Da Prato and Debush gave a construction which is in some sense more robust than the one by Röckner and Albeverio. Okay, so the construction by Da Prato and Debush didn't use anymore that the measure was equivalent to the Gaussian measure, for example. And it gave a notion of solution for every initial condition, whereas in Albeverio and Röckner, they only had a notion of solution for almost every initial condition with respect to the invariant measure. Okay? And so what I want to essentially what I want to explain in these lectures is how you can give a robust solution theory for these equations in dimension 3. And in a way which is sort of as intrinsic as possible. Okay, so you would want to have a notion of solution for which maybe you know that some regularized versions of the equation converge to it, but you wouldn't want your notion of solution to depend on some regularization, right? You want it to be some kind of intrinsic notion, which doesn't depend on how you regularize things. And now the technique that I'm going to use to show that is quite a general technique. Okay, so it's not something which is tailored to these two equations in particular. So you can use it for a number of other equations, so like KPZ equation, which we have also some work in progress with Jeremy, and there's some previous work on mine where I make sense of KPZ equation using that technique. But it works also for a number of other equations, so there's quite a large class of nonlinear stochastic PDEs to which you can apply it. So a large chunk of the technique doesn't really depend on this particular form of the equations, but then some of the details of the implementations do, and so I want to focus on one example so we have something concrete in mind. Okay? No. So in particular, it's not. So that's not important at all. Don't use reversibility at all. For KPZ, for example, you don't have reversibility. That's right. So for example, here you could easily have more than one component, and then you could replace this by any polynomial of degree 3, and it just has to be, well, yeah, so it could be any polynomial of degree 3 here. And the solution theory is local, so in a way, it also gives you local solutions for this, but then of course they wouldn't be global. That one would blow up in finite time. Right? Sorry?
You're going to state what you...
I'm going to state for them, yes. Right, so here is what you can prove, right? So you take a regularization. So take a space-time regularization of the noise. Okay? So I take a psi epsilon, and I regularize it in such a way that ys is equal to some function of, so I do a regularization which is adapted to the parabolic scaling here, but that's not absolutely essential in principle. So I put a t over epsilon square, x over epsilon, and then here you have to put an epsilon to the -5 because we're in dimension 3, so this looks like a delta function. Well, of course, this is t minus s, x minus y. Okay? So this now looks like a space-time delta function. Okay? So you take a regularization of this type. So for every epsilon, psi epsilon is a random smooth function. And you choose your constant c epsilon here in exactly the way that I mentioned here. Okay? And so then the theorem here is that you look at this sequence of the sequence of solutions, and you get a weak limit as epsilon goes to 0 on as kind of space-time distributions or functions of time with values in distributions in space. And the limit does not depend. It does not depend on the choice of this function rho here. And furthermore, there's a description of the limit, which doesn't, right, it doesn't see any regularization anymore. Okay, so there is if you want a direct description of the limit as a solution to a fixed point problem, essentially you want to build a usual kind of PDE theory for these type of PDEs. Okay? So you would want to say, well, the solution of this equation here is the solution of some fixed point problem, which looks like what you do when you solve a PDE by Picard iteration. Okay, so you would want to rewrite this as an integral equation. You want to make sense of all the terms in the integral equation, and then you want to get a local solution theory. Sorry?
T is global?
Right. So you really view it as a PDE, as an initial condition problem. Okay? So now you have an initial condition at time 0. So at time 0, you're allowed, so you take an initial condition, which is not allowed to be an arbitrary distribution, of course, because even if you didn't have that guy at all, the deterministic equation wouldn't make sense for an arbitrary distribution as initial condition. Okay, so you can take the initial condition in pretty much the largest space for which you can make sense of the deterministic part of the equation. Okay, so I'm going to write here, say C alpha for alpha bigger than minus 2/3. Okay, and so what does that mean? Well, you should kind of think of it as apply the so here it's a C alpha with negative alpha. Okay, one way you can view this is apply the inverse of the Laplacian to this. Okay, then you get a function, and that function should be C 2 minus better than 2 minus 2/3, so it's sort of 4/3. Okay, so and this is sufficiently, you allow for sufficiently irregular initial conditions so that the solutions have better regularity. Okay, so you can really set up a PDE theory with maximal solutions. Okay, you can restart, you can solve it locally, and then you can evaluate at the end point, and you can take this as an initial condition for the equation again, solve it for a bit. Well, so this a priori you don't know. So this you have to use other a priori knowledge that it doesn't blow up. Like, for example, knowing that it has an invariant measure. So then you would know that almost surely it doesn't blow up. But so you don't.
The way you describe it, you want to conclude something about the measure dynamic.
Right. So here is the kind of things that you could conclude. So, for example, you take the. There is a very nice paper by Bridges, Fröhlich, and Sokal, where they look at a lattice approximation to this 543. Okay, so you do this whole thing on the lattice, you do the natural discrete approximation, and then they have very good tightness bounds, right? So they prove that the sequence of measures that you get is tight in some very strong sense. And so now, using these a priori bounds, so now you could imagine taking a lattice version of this equation. Okay. Now you would want to show that your lattice version of the equation converges to this limiting object. So now that's not included in this theorem, okay? But certainly the technique allows for these kind of statements. Okay, so now you have your lattice dynamic that converges to this limiting dynamic. You have very good a priori bounds. And then you know that any limiting measure that you get from these a priori bounds has to be an invariant measure for this limiting dynamic that you can describe a priori. Now, if you can show that this limiting dynamic has a unique invariant measure, and this one has the techniques to do it, so there's certainly strong belief that this is strong Feller and irreducible, and so it would immediately have a unique invariant measure, then it immediately tells you that the tightness that people obtained was actually a convergence. Right? And in particular, it tells you that it was a convergence to an object which doesn't make any reference to any kind of lattice approximation. So which tells you that then if you actually did another kind of regularization, you get the same object in the limit. Okay, and at least to my knowledge, there's no proof that these different approaches to these 543 measures really give you the same measure. So there's a way of showing that they're actually the same. So that's one way of going back and forth.
I'm confused. So does this dynamical approach allow us to establish the different ways of constructing 543
I think in principle it allows you. Now, there's certain, I mean, it doesn't follow from what's been done at the moment, right? So it doesn't follow immediately as a corollary. But certainly the tools are there, so in principle it should work. Oh, right. So here you have to choose the C epsilon potentially like this. Right? So if you want to get a limit as epsilon goes to 0, you have to choose the constant C epsilon in that way.
You got two-dimensional,
Three-dimension.
So
So phi is in three-dimensional, and t is an extra.
T is an extra
So
dimension.
it would be like
Right.
going to four-dimensional field theory.
Well, not really, because it's not, that doesn't behave like the time in a QFT. Right? It's not the same thing.
So there's no other realizations in the
No, so here there's only this.
constant or
Well, okay, so this here is what people call this additional mass renormalization, right? So if you do the usual Wick product kind of renormalization, that would just give you this, and there's this additional logarithmic
so
divergence.
so the Φ4 is no realization.
Right, so
You don't need
you only need this, yeah. And this was, of course, well
In
known.
other problems, do you need renormalization beyond the ones that are required for the invariant measure? In other words, the invariant measure, of course, has a big order bubble counter terms.
Mm-hmm.
But dynamically, you might imagine you might even need additional counter terms, but you don't need them.
Yeah, here you don't need them. That's
Here,
right.
I understand, but are there other examples where you do need it?
I don't know of one, but I don't know. I don't know if that's a. I don't know if that's a general one. One could certainly imagine, yeah, but I don't know. Yeah, I don't know.
A lot of these methods depend on the Φ4 is a small coupling constant quantity.
Mm-hmm.
If your method depend on the coupling
No,
constant
so here it doesn't. So but you get local solutions, right? So if you want to know that your solutions are global in time, then you need to have some other a priori knowledge, right?
small time.
And then you would. So it's kind of, yeah. So in some sense, small time replaces small coupling constant.
But don't you have global existence in time for these?
Well, you don't know a priori, right? So it's very difficult to get a priori bounds on that. If you know the invariant measure and you really know that, so the thing is that you have to first prove, right, that if I do this kind of regularization, I don't have any formula here for the invariant measure. It's not a gradient type anymore. Right? So with this type of regularization, you don't a priori have a handle on the sequence of invariant measures, and you need a very tight handle. So that's why. So that paper. That's why that paper by Sokol, Bridges, and Fröhlich, there they have a very good handle on it for this lattice approximation, and they have a handle in these kind of spaces. They have tightness in these kind of spaces in which I can actually start in it, which I can take as initial condition.
You can
right?
do that too there.
So
I mean, that's a different regularization.
it's a different regularization because it would be a lattice regularization in space. So one has to fiddle around a bit in order to make this lattice regularization fit into the framework.
Go two dimensions or even one dimension, then this, everything works okay. I mean,
Yeah.
then you know exactly what you're doing, like in one dimension.
Yeah, well, so in one dimension, there's no need for any kind of randomization, right? So in one dimension, you don't need that constant at all, and it's easy to get a priori bounds on the solution, and so it's trivial to show that you have global solutions. In two dimensions, you have a log here, and it's more difficult to get a priori bounds, okay? But it's still possible.
The invariant measure is unique, or whether you are in the phase transition.
Well, it's in finite volume, so you would only expect it to be. You would always expect it to be unique here. Okay. Yeah. Okay. So, right. So let me try. So how long do I have actually until the hour? Okay. Yeah. So let me try to give you a flavor now on how you prove these kind of results here. Okay. Also, what's the technique of proof? So the idea is you really want to set up some kind of a PD technique. Okay, so you want it to be essentially a pathwise construction. And you don't want it to rely on statements like, absolute continuity of the law with respect to something that you control or things like that. And in principle, you don't even want it to rely on an invariant measure at all. So you want to, for example, like Herbert was saying, so you could take could take a polynomial which is not of gradient type, and then you wouldn't have any formula for the invariant measure. And of course, the problem is that solutions are very singular. So the typical regularity of the solution, so you would never expect the solutions to anything like that to be better than the solution to the equation where you've just removed the nonlinearity, right? So if you
just want to prove that the existence of Φ43 dynamics, even the Gauss dynamics is much easier.
You mean between this one and this one? No, it makes no difference. Yeah, so that's they are not, right. So none of them is somehow obviously easier than the other one. So it's essentially the same. Okay, so let's just try to guess what's the regularity of the solution. Okay, so just to get some practice. So how regular is this psi? So as a space-time distribution. Okay, so as a space-time distribution, remember psi is essentially defined as, well, let me put a square here. Okay, so if I test psi against the space-time test function, and I take the expectation of the square, I just get the L2 norm square of the test function. Okay. What it means is that if I take an f delta, say, which is something that looks like a delta function, okay? So I take a bump function and then I rescale it so it looks like a delta function. And I do it with the parabolic rescaling. Okay, so f delta of x and t would be, well, something like here, right? So delta to the minus 5, f of x over epsilon t delta t over delta square. Okay, so you do something that looks like a delta function. Then, well, you see that here you get a delta to the minus 5, actually, for the L2 norm. Okay, so that's a simple, easy calculation, just a scaling argument. Now, there is a characterization of these kind of negative Hölder spaces, if you want, in terms of the magnitude of what you get when you test a distribution against a test function that looks like a delta. Okay? And so what this tells you is that psi essentially belongs to c to the minus 5 half, and it actually doesn't quite belong to this c to the minus 5 half, but it belongs to c to the minus 5 half minus kappa for every kappa. Right? So that's exactly like Brownian motion. When you do the expectation wt minus ws square, you get t minus s, which sort of suggests that it would be Hölder half, but it's not quite Hölder half. Okay, so you know that almost surely it's not Hölder half, but it's Hölder anything below a half. So it's exactly the same story here. Okay, so this guy has regularity essentially minus 5 half. And so therefore, what you expect for phi, well, the heat equation makes you gain 2 degrees of regularity, right? And so you would gain 2 degrees of regularity starting from minus 5 half, so you end up in minus 1 half. Right? Okay, so you would expect phi to be a space-time distribution that in this parabolic regularity sense has regularity minus 1 half. Okay? And so it's really quite far from being a function. And that's essentially why the, in the phi cube, you have to renormalize it in some sense. Now, so in general, you know that, well, you're simply not allowed to multiply distributions. If you have 2 arbitrary distributions, there's absolutely no way of defining a meaningful product between them. And so the idea is to, well, you have to encode additional information. Okay? So the aim of the theory is actually to set up a framework in which the solution phi, in some sense, behaves as if it were a smooth function. Okay? But now, what does it mean to be a smooth function? So classically, being a smooth function means that you can be approximated up to order, whatever the degree of smoothness is, by a polynomial. Okay, so it means you can find around each point, you can find a polynomial, which is your Taylor polynomial, so that the difference decays at an order, which you call then the degree of regularity of your function. Okay? And so in this case, what you want to do is if you want to introduce a purpose-built notion of smoothness. Okay, so you want to measure the regularity of your distribution phi in a way which is not comparing it to polynomials, but is comparing it to objects that are purpose-built, that sort of, are built in a systematic way by using the kind of algebraic features of your equation, okay, and allow you at each point, around each point, to describe, to give you some approximation of the solution phi up to a certain order, which we would then call the regularity, if you want, of the solution. And the point is you want to be able to build these objects a priori, right, before having actually solved the equation. Okay, so you want to first build these objects that are going to play the role of polynomials, but they are going to themselves not be smooth functions at all, so they are going to be distributions typically, because phi is a distribution. Okay? And then you want to recast this equation as a fixed point problem in a space of distributions that are locally described by linear combinations of these objects that you've built. Okay, so in the same way as you would usually set up a fixed point argument.
X, right?
Yeah. No, this is in space-time, in x and t. Actually, right, so that's actually a very good remark. The right-hand side, this minus phi cubed, does not make sense for fixed. So for fixed t, it doesn't make sense as a distribution in space, but it makes sense as a space-time distribution. So yeah, so you have to formulate it in space-time because otherwise you can't make sense of the right-hand side. Okay. And now the other problem here is that the equation that we're really looking at is this equation. Right? So which really means that we're not looking at one equation. We're really looking at a sequence of equations. Okay? So in some sense, this guy, you would think it's sort of harmless, the fact that it's a sequence, because it's just an input to the problem. Okay? And then you would say, well, this input has to converge in the right sense, and then the solutions will converge. But this constant here is a problem, right? So it really changes the equation. You're really looking at a different equation at every epsilon. And so you have to somehow disentangle that. And so what's going to happen in the end is that as far as the equation is concerned, the equation we're going to look at is the one where this constant isn't there at all. Okay, or it's set equal to 1 or some fixed value. It doesn't matter. Okay, say you don't have it there at all. So you really look at this equation here. Okay? But then this renormalization business is all going to happen at the level of the construction of these objects that are going to play the role of polynomials. Okay? And then what's going to happen is that at the level of these objects, there's going to be a product defined between these objects. And it's just that even for fixed epsilon, that product might not coincide with the usual pointwise product between functions. Okay? And then you can actually go back at the level of, once you've constructed your solutions, you can go back and you can ask yourself, which equation did this actually solve? And so if your product didn't coincide with the usual product, well, that means that the equation that you actually ended up solving wasn't the equation that you had the impression you were solving. It was actually a different equation. right? And so that's how, what you realize is that you were actually solving this equation all along, even though you were kind of thinking that you were solving a fixed equation which didn't depend on epsilon. Okay, and then you show that all of the objects that you build, so that the solution theory, the solution is continuous as a function of, well, basically everything, as a function of the initial condition and also as a function of these objects that play the role of polynomials. Okay, and then once you have this continuity, all you have to do is prove that these objects converge to a limit, then you automatically get convergence of the solutions. And these objects are just going to be finitely many objects. Okay, so that's going to be like 5 or something. So there are 5 objects of which you have to essentially by hand prove that they converge in a suitable topology, and then your solutions converge automatically. Okay. So I have 5 minutes. Let me just draw a cartoon of how this works. So here you'd have, so the usual solution map. So let me write SC for the classical solution map. So the classical solution map to, say, a PD of this type, well, so you view the noise as you view a fixed realization. You view it as just a random, a deterministic smooth input. Yeah. Okay, so that one takes as an input, well, it takes an initial condition, phi 0, which would belong to this C alpha space. And then it takes, at least for fixed epsilon, it takes the noise, which would be, so for fixed epsilon, that would be, say, a continuous function, okay, space-time. But then in this case, as I just mentioned, it takes also a third argument, which, well, in this case, would be the value of this constant here. Okay, so there's a third argument which tells you which is the equation that you're actually solving. And that depending on the, so here you have the sort of right-hand side of your equation that takes values in something. So in this case, well, the right-hand sides are parametrized by one constant. Okay, so there are other examples where this could be more complicated. So the right-hand side could be parametrized by a bunch of nonlinear functions, for example. Okay, so this could be something more complicated than just one constant in general. And then what you do is you lift this to a fixed point problem in this space where you describe everything locally in terms of these objects that are going to play the role of polynomials. And these objects are going to be built from the noise. Okay, so there's going to be an arrow going up here that builds these objects. So I call M here a space of what I call a model. So a model would be a collection of objects that plays the role of polynomials. Okay, think of it in that way. And so typically for a smooth realization of the noise, there's going to be a canonical way of lifting it, and that gives you a model. And then it's going to still take as an input the right-hand side and an initial condition, and they don't change. So, right, so then you have a solution map up there that's going to live in some space, which I call sort of D gamma, and that would be like a C gamma space, except that instead of describing things up to order gamma by polynomials, we describe it up to order gamma by the objects that live in here. And then here there's an operator that goes back and turns this into an actual distribution or function, in our case, distribution. Okay? Now, this you can make it such a way that it commutes. And furthermore, these two arrows are continuous, and you have very good control on how continuous they are. They are essentially locally Lipschitz continuous in the correct kind of topologies. Okay, so here everything is nice and locally Lipschitz continuous. Here we know that things are not going to converge, right? So if you fix the right-hand side and you just send epsilon to 0, things are going to diverge, right? So that means that this guy is badly discontinuous. Okay? And now what's going to happen is that the construction comes with also a group of transformations that act on that space. Okay? So there's going to be a finite dimensional. It's actually going to be, yeah. So it's, as an abstract group, it's just going to be a finite dimensional Lie group. Oh. Right. Well, so in this case, right. So here I don't have really a good description of the whole thing. But then the subgroup that we need is something completely trivial, because the subgroup that we need is just, as a group, it's just R2 with addition, actually.
So it's not something to do with centering things or some kind of centering masses?
It has to do with centering things. Yeah, it does have to do with centering things. It's just that in this case, as a group, it's very trivial. So it's just R2 with addition. And the 2 really comes from, that constant had really 2 bits. There was the 1 over epsilon bit and the log epsilon bit, and they really show up as 2 completely different constants. Yeah. So this is, in our case, this would be R2. You can think of it as R2 acting on this. And that changes, you want this model. So every element of R2 here is some kind of recentering, as you say, of the model. And then it comes with a dual action on the right-hand side here. Okay, and so that's which makes the picture commute again. Okay, so in the following sense. So you take a smooth function, you take an element here of R2, which essentially is just 2 constants. You take a smooth function, you lift it up here, then you act on it with this element on R2, so it just shuffles around these objects. Then you plug this into this solution map, and you project it down. This gives you a function. For fixed epsilon, it just gives you a smooth function. And that function is exactly the same as that you get by classically solving the modified PDE, where now your right-hand side has this constant in it instead of being just this right-hand side, right? So up there, the right-hand side formally would be this. And down at the bottom, after acting on it with this group element, which is star 2, all it does here is that it adds this constant. Okay? And now, essentially, the problem is just once you have this, okay, and this is a completely general thing. So this is a very general thing that doesn't have much to do with this particular equation. Okay, so there's a simple power counting thing that kind of tells you whether you can recast an equation into this framework or not. Okay? But it works for a very, very large class of PDEs. And then the problem is, can you exhibit a sequence of elements here? Sorry? It is parabolic. Or elliptic. Could be elliptic, actually. Right, so then the problem is, can you find a sequence of elements here so that if you lift your regularized noise and you act on it, you make it converge in this space. Okay, and it has to converge in the topology of that space. And then that's something that is actually not that difficult to check by hand in this particular example. Okay, okay, so I think I'll stop here for today. So then the remainder of the lectures will be, well, essentially tomorrow I want to explain a little bit the general theory, which doesn't have much to do with Φ4. And then on Thursday, I want to go back to Φ4 and show how do you actually prove convergence of these objects. So what's the kind of things that you have to check.